Our next titration we're going to look at, we're just not going to spend hardly any time on. What if you had mixed it up? What if you had put the sodium hydroxide in the Erlenmeyer flask and had our strong acid, our HCl? So this point where at this one we are titrating a strong base with a strong acid. Well, since we're always looking at the pH of the solution down in the Erlenmeyer flask, and that's where the base is, it's going to start at a high pH. And we could do all the calculations again, we won't, but you'll find that the curve is going to look a lot like the strong acid, strong base titration curve. It starts out flat, but at a high pH, because Erlenmeyer is basic. Then we get this drastic lowering of the pH as we get a little excess acid, and then it flattens out again. And since it's strong acid, strong base, at the equivalence point, there is nothing except for water determining the pH of the solution, and the pH is 7. But now we're going to have some fun, and it's going to start out looking kind of nasty, but there's going to be some fun stuff that'll help us out. Now let's look at a titration of a weak acid with a strong base. Starts out gnarly, but I'm sure you'll be able to handle it. Let's put in a weak acid, let's say 0.1 molar acetic acid, 50. Let's put in 50 milliliters of 0.1 molar acetic acid into the Erlenmeyer flask. And let's have our 0.1 molar sodium hydroxide in our burette. We're going to do the same thing. We're going to calculate the pH at various volumes of NaOH added. Note, we can already tell since our concentration of acid is 0.1 molar, our concentration of base is 0.1 molar, the fact that we have 50 milliliters of acid tells us it's going to take 50 milliliters of base to do this neutralization. The difference is this is a weak acid. And some interesting things we might want to know. The Ka of acetic acid, 1.8 times 10 to the minus 5. Negative log of Ka is pKa, and it's 4.74 for acetic acid. That will be necessary starting at the first calculation. Before we add any sodium hydroxide, what's the pH inside this weak acid? Oh no, it's a weak acid. It's not a strong acid that dissociates 100%. It's a weak acid. From now on, we're going to call it HA, so I don't have to write all this out every single time. It's going to be called HA. It's a weak acid. How do you determine the pH if you have a weak acid? You need an ice table. Yay, yay, lots of ice tables. We love ice tables. All right, so we know if we just have our acetic acid, HA will dissociate in H plus A minus, ICE, draw the line, because it's equilibrium we're after now. We start with 0.1 molar. Recall with ice table, it's in molarity. Moles per liter, molarity, 0.1 molar. Before any dissociation, no H plus, no A minus, minus X plus, 0.1 minus X, and X. Plug these into our Ka equation that we know is a concentration of H plus times concentration of A minus divided by concentration of HA. 1.8 times 10 to the mince fifth. Our Ka equals X squared of 0.1 minus X. Can we ignore the minus X? 10 to the minus fifth, yes. So our concentration of, our value for X here, which while it is the concentration of A minus, is also the concentration of H plus, and it's the H plus that determines pH. Concentration of H plus is 1.3 times 10 to the minus third, our value for X. Take the negative log of that, and our pH is 2.87. Before we add any base, we're at a pH of 2.87. Now, let's add 10 milliliters of base and see what happens. Well, the first thing we have to ask ourselves, we add 10 milliliters of base, what's the base going to react with? Well, the base will react with our acid that's in there. We've got acid in there, the weak acid, the base will react with it. Recall, when you have a weak acid and a strong base, that's a 100% reaction. This is not an equilibrium with a strong base and weak acid. This is 100%. Since it's not equilibrium, this is a stoichiometry calculation. ICF, final is the way to go. We don't have to worry about X's or anything. This is just stoichiometry. Note, we start out with 5 millimoles of HA. Recall with ICF type tables, you need millimoles, not molarity. So we had to take this 0.1 molar HA times 50 milliliters to get 5 millimoles of HA. The amount of OH minus, 0.1 molar times 10 milliliters is 1 millimole of NaOH. We see we've got a 5 here, a 1 there. Sodium hydroxide is a limiting reagent, so all of that will be used up. We'll subtract our 1 millimole from our 5. We get 4 millimoles of HA. no NaOH, and we've got our plus 1 millimole of A minus, because our 1 millimole of NaOH reacted with 1 millimole of acid to make 1 millimole of the conjugate base. Well, now we need to know the pH in here, but what all do we have in here? Well, we don't have any excess base, strong base, none of that, but we've got weak acid, and we have its conjugate base. We have a mixture of a weak acid and its conjugate base. Awesome. That's a buffer solution. And why do we love buffer solutions so much? Because we can use Henderson-Hasselbalch equation to get the pH, and that makes us happy. So our pH is just pKa plus the log of the amount of A minus divided by the concentration of HA. pH is 4.74 plus log of 1 divided by 4. Take 1/4, log of it, add it to the 4.74. Our pH is 4.14 at this point. Cool. And while it looks kind of nasty to begin with, we tend to like our weak acid strong base titrations because we can use Henderson-Hasselbalch as long as we have a weak acid that has a very small Ka value, 1 times 10 to the minus 4th or smaller, which most of them do, so we are good with that. All right, next calculation. Let's add 25 milliliters of NaOH. Note, we had a calculator, we're going to have a total of 50, so we're halfway when we have the 25. Note, we first have to see what happens with the NaOH when it reacts with the HA, so that's an ICF type table here. We'll have no NaOH left over. We've got 2.5 millimoles of HA. We'll have 2.5 millimoles of A minus. Recall that in the Henderson-Hasselbalch, since volumes cancel here, you can just put the moles in there. We learned that in the buffer section of this chapter. pH is 4.74 plus the log of 0.25 divided by 0.25. Well, 0.25 divided by 0.25 is 1. The log of 1 is 0. 4.74 plus 0 is 4.74. The pH is 4.74. Note, volume-wise, important, volume-wise, we're halfway. We knew we were going to have to add 50 milliliters. We've had 25 milliliters. We're halfway. We call, volume-wise, we're halfway. We call this the half equivalence point. When you're at the half equivalence point, when you've added half the volume that's necessary, pH equals pKa. So that's a nice thing to know. Let's continue on. We're going towards 50. Let's add 40 milliliters of NaOH added. We do up our table. NaOH is still limiting reagent. We've got 0.1 millimoles of HA left over. We've got 4 millimoles of A minus in here. Just to reiterate something, when we're doing the strong acid, strong base, we didn't care about A minus because A minus was chloride that did not affect pH. With a weak acid, we know the conjugate base of a weak acid is a weak base. We know that A minus here, or NaA, does affect pH, so we have to take care of it. We have to include that in here. All right, but we still have a buffer solution. We still have HA, we still have its conjugate base. Henderson-Hasselbalch, pH is 5.34. 45 milliliters of NaOH added. Do the calculation again. We've got 0.5 millimoles of HA. We got 4.5 millimoles A minus. Buffer solution. Henderson-Hasselbalch, pH is 5.69. Ooh, man, can you imagine if this were a homework or problem? How long would it take you to do this? A long time. All right, so let's add 49.5 milliliters of NaOH added. Whew, HA plus OH minus, the whole works again. Note 4.95 millimoles of OH minus. We always start with our 5 millimoles of HA. And OH minus is still the limiting reagent here, so all of it's gone. We've got 0.05 millimoles of HA left over. We've got 4.95 millimoles of A minus. We still have a buffer solution. Henderson-Hasselbalch, pH is 6.74. I'm not going to do 49.9. Let's just jump to 50. Because here's the deal. When you jump to 50 milliliters, when you're at the equivalence point, this next thing that we're going to do is really an indicator if you understand titrations, if you really understand these pH titrations. This one problem right here is essentially a review of this chapter and the previous chapter. Let's look at this. All right, just to give you a hint, we're trying to find the pH of the solution after 50 milliliters are added. It's not even on the page. It's down here somewhere. Not too far, but it's down here somewhere. We haven't gotten to it yet. This is a bit involved, so let's go through it. 50 milliliters of NaOH added. Our NaOH is going to react with our HA, so we can do our ICF table here. Note, we added 5 milliliters of NaOH. We start with 5 millimoles of NaOH. We start with 5 millimoles of HA. We have no HA, we have no OH minus left over. All we have is 5 millimoles of NaA, of our A minus, of our conjugate base. But recall, this is the conjugate base of a weak acid, and the conjugate base of a weak acid is a weak base. We don't have any HA left, so we don't have a buffer solution anymore. We cannot use Henderson-Hasselbalch. All we have in solution now is sodium acetate, the conjugate base of acetic acid, and the conjugate base of weak acid is a weak base. So how do you find the pH if you have a weak base in solution? Ice table. We're going to have to go back to an ice table. We can't do Henderson-Hasselbalch. We know that we've got the conjugate base, NaA. That's our only thing. We've got NaA in water. We know that A minus, or sodium acetate here, will react with water to form HA plus NaOH. That's an equilibrium reaction. Note, this is an ice table. We need molarity. We have to have our concentration of A minus, our concentration of sodium acetate in units of molarity. So we had to take our 5.0 millimoles divided by our total volume, 100 milliliters, to get 0.050 millimoles per milliliter, which is molarity. All right. Note, this should make sense since we started with 50 milliliters of acid, added 50 milliliters of base. We've got 100 milliliters total. The concentration of A minus that's left over is half the concentration of our original amount of acid because the volume is doubled. All right. So, ice tables, we've got the 0.05 molar A minus, 0.05 molar. We're not going to worry about the water. Before any dissociation, no HA, no NaOH. The change, minus X plus X plus X. It's equilibrium, so we don't know these volumes, or these amounts. Have to use the X's. Equilibrium, 0.050 minus X, X, and X. But note, this is a base. So this is a Kb reaction, a base plus water. This is Kb. And we weren't given the value for Kb. We were given the value of Ka, 1.8 times 10 to the minus 5. How do we calculate Kb that we need for this reaction? Well, recall Kb equals Kw divided by Ka. 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5, our Ka. Our Kb is 5.6 times 10 to the minus 10. So we can plug that in here. 5.6 times 10 to the minus 10 equals x squared over 0.50 minus x. Our HA is x, our NaOH is x, and our NaA that we start with is 0.5 minus x. Can we get rid of this minus x? Oh, you betcha, with a 10 to the minus 10th here. We can definitely get rid of that minus x. We solve x is 5.3 times 10 to the minus 6. And that's our concentration of sodium hydroxide, left over. But note, that won't give us pH. pH is a negative log concentration of H+. However, we take the negative log of 5.3 times 10 to the minus 6, and that'll give us the pOH, which is 5.28. Subtract that from 14. pH is 8.72. Very important point to note here, at the equivalence point of a weak acid strong base titration, the pH is not 7. At the equivalence point of a weak acid strong base titration, we have leftover conjugate base, which is a weak base. Therefore, we're going to have a pH greater than 7 at the equivalence point of this titration. Well, let's keep adding some more base, and we're not gonna go as crazy as we did with a strong acid. Let's just do one more time. Let's add 60 milliliter total of NaOH. And with 60 total milliliters of NaOH, that means that, okay, now we've got we've got 6.0 millimoles of OH, 5 millimoles of HA. HA, our original acetic acid, is now our limiting reagent. There's none of that left. We got 0.1 millimoles of OH minus left over, but nope, we also have 5 millimoles of A minus. So we've got a strong base, our OH minus, and we've got a weak base. How do we determine the pH? Recall from buffer solution, anytime you have a strong base and a weak base mixed together, it's the strong base that determines the pH. So our concentration of OH minus is going to be 1 millimole divided by 110 milliliters, our new volume. So that's 9.1 times 10 minus third molar. pOH is 2.0. pH is 12.0. All right, so what does that titration curve look like? If we plug in our values, we get a titration curve that looks like this. And note, it starts down here and it's going to rise a bit and then even out, then get fairly horizontal. And when we start getting to the equivalence point, we have a more gradual upslope here. And then it goes through the equivalence point. And then we have a more gradual, or actually a sharp change, because a sharper change here. This part is a little bit more gradual than you see with strong acid, strong base because of the buffer solution. But once we get back up here where our pH is dominated by the strong base, so this is a little bit sharper due to strong base. All right. But it also recall with a strong acid, strong base, the curve started off nearly flat. It started going off this way, like this, and this one starts up. A few things to note, as we mentioned before, at the equivalence point, we are basic. We are not at a neutral solution because we have base left in there, and something, or because we have conjugate base, which is a weak base. And as we mentioned before, that at the half equivalence point, if the equivalence point is 50 milliliters, then half 50 is 25. Recall at the half equivalence point, pH equals pKa. But this whole area right in here, we call this the buffer region, because we can use Henderson-Hasselbalch. We have a buffer solutions here, and which means if you have a weak acid and you're titrating with weak base, the pH is just not going to change that much throughout this area right there, these volumes of NaOH due to the buffers. All right. And this video is a little long, but before we leave it, a note, when we did these last two titration calculations, we knew the concentration of acid, we knew the concentration of base, we knew the volumes, so we were just using this to calculate our pHs. What's normally done in a lab is you might have some unknown weak acid. I know this is a weak acid, it reacts with base, but I don't know what weak acid it is. I have no idea what this stuff is. So in the lab, what you do is you'd weigh out that acid, because if you weigh it out, that gives you the grams of acid. Dissolve that in water. After you put that in the Erlenmeyer flask. Then you do a titration, and you titrate the NaOH with a known, shouldn't say quantity, a known concentration of NaOH. Because we will know the quantity at the end, but we do a known concentration of NaOH. And we add a little bit of NaOH at a time, and what you would do is you'd stick a pH meter in that Erlenmeyer flask. So you would monitor the pH, add a little bit of sodium hydroxide, monitor the pH, add a little bit more sodium hydroxide, monitor the pH. And then you can actually plot your titration curve, because you said, okay, I added 1 milliliter, here's the new pH, plot that. Added 10 milliliters, here's a new pH, plot that. 11 milliliters, however you want to go, and you actually plot out the titration curve instead of calculating it. Can't calculate it because you don't know what the pKa of your acid is. You have no idea what it is. But you plot out that titration curve. And then you realize that as you do this titration curve, eventually you come to the equivalence point where the moles of acid equals the moles of base. Well, before you had the grams of acid, now you know that grams of acid is this certain moles of acid. Well, moles is grams divided by molecular weight. So by weighing out your grams of acid and titrating it to find the moles of acid, you now have the molecular weight of your acid, which is pretty cool. All you have to do, if you hear some unknown acid, what is it? Well, I don't know. Let me titrate it with base, and boom, you've got the molecular weight of that acid. Not only that, after you do the titration, you find the equivalence point, go to the half equivalence point, go up to this layer here, this level of your curve, and go over, and now, oops, down here, this over here, and now you've got the pH at the half equivalence point. But what do we know about the pH at the half equivalence point? That's the pKa. So now not only do you have the molecular weight of your acid, you have the pKa of your acid. Look on a table of various acids, and I bet you can figure this out. And that's pretty good if you just have some unknown acid and you just get some sodium hydroxide that is cheap, a burette, do this titration, get a pH meter, and now you can figure out the molecular weight and pKa and figure out what your unknown acid is. I think that's a pretty nice thing.